Okay, now let's come back to our system. We consider this system and we substituted this solution into the system, and now we know how to find R and U. And as you remember, in previous lecture we realized that if A, for example, is 3 times 3 matrix, then we need to find three linearly independent solutions. 3 linearly independent solutions to obtain the general solution for the system. And as remember, general solution is just linear combination of these three linearly independent solutions. This is just a reminder from previous lectures. And now, as we noticed that if A, for example, we considered A 3 by 3 matrix has 3 different eigenvalues, then we can get 3 different solutions, right? We can get 3 different eigenvalues, 3 different eigenvectors, so 3 different solutions. The question is, are they linearly independent solutions? So there is a theorem, first of all, that if R1, R2, and so on, we now consider general case, Rn are distinct. This is very important here, distinct eigenvalues of A. Then, and U, I are eigenvectors corresponding to each eigenvectors corresponding to each eigenvalue Ri. Then this set of eigenvectors u1, u2, and so on, un, is set of linearly independent vectors. So to prove, we first assume that n equals 2, so we have just 2 vectors here. So let n is 2. And we need to prove that these 2 vectors are linearly independent. So we assume the contrary, that these are linearly dependent. 2 vectors are linearly dependent. It means that one vector is a constant times another vector. And we also know about these vectors that they satisfy that A u1 is the corresponding eigenvalue times u1, and A u2 is corresponding eigenvalue times u2. And let's start with R1 u1. We know that this is A times u1, and we know that u1 is C times u2 from this equality. And AU2, we know that this is R2U2. And CU2 come back to U1, so this is R2U1. So it means that R1U1 is equal to R2U1, and we can move this thing to the left side and take out u1, take out of the brackets, and this must be 0 vector, right? And since u1 is non-zero, vector, this is eigenvector which is non-zero, right? It follows that that this coefficient must be 0. R1 minus R2 must be 0. So R1 must be the same as R2. But we assume that the eigenvectors are distinct. So this is impossible. So U1 and U2 are linearly independent. They are linearly dependent is not possible, so they are linearly independent. And the same thing, to prove the same thing for arbitrary n, you can use induction. I'm not going to write details of the rest of the proof. Okay, so what we know now? We know that now if we have distinct eigenvalues of n by n matrix and ui are corresponding eigenvectors, we know that this set of eigenvectors is linearly independent set. Now we can prove the following theorem. If n times n matrix A has n distinct, again it's very important here, eigenvalues and eigenvalues say R1 and so on Rn, and U1 and so on Un are corresponding eigenvectors, then the general solution of the system, of the homogeneous system x prime t is a x t is x of t is c1 e to the r1 tu1 plus c2 e to the r2t u2 plus so on plus cn e to the rn t un. Let's prove it. As remember from previous lecture, to find the general solution of the system, we need to find n linearly independent solutions, right? And this theorem says that these linearly independent solutions are exactly these functions here. So we have to prove that the set E R1T U1 and so on E RNT UN is the set of linearly independent vector functions. How we prove this? We will find Wronskian of them, right? So the Wronskian of these things at a point T is the determinant of this. The determinant of this vector functions e to the r1t e to the r1t u1 to the r2t u2 and so on e to the rnt un. And the determinant has the property that we can take out of the determinant the multiple of each column. So U1 now is the column of the matrix, right? And the multiple of this column is e to the r1t, so it can be taken out of the determinant. The same for the second column, and so on, multiplied by the same to the nth column. And we leave the determinant of U1, U2, and so on, un. And this thing is non-zero, right? So of course, for any t, this is non-zero. And the determinant is non-zero from the previous theorem. We know that u1 and so on, un, are linearly independent. And as you remember, if the columns are linearly independent, then determinant is non-zero. This is theorem from the first lecture of previous week. So this one is non-zero, this one is non-zero, so overall this is non-zero. It means that this set is indeed linearly independent. This set here is indeed linearly independent. So the theorem is proved. So this theorem gives us the precise formula for general solution for the homogeneous system, but in the case when A has n distinct eigenvalues. So to find general solution, we have to find eigenvalues and eigenvectors of the matrix A. Let's consider an example. For example, we are given this homogeneous system and also the initial value. So let's solve this initial value problem. And this matrix is exactly the matrix that we considered in previous video, and we already found for this matrix eigenvalues and eigenvectors. And let's now write general solution for the system and then apply the initial value to find precise constants. So general solution is C1 times E to the R1, so R1 is 1, just T, times U1, and U1 contains this parameter S. This parameter S will go to this constant C1, so we can just ignore it, or we can say we take S to be 1, since this variation of S is already here in C1. Since we have C1. So we just write minus 1, 1, 2, plus C2 e to the second eigenvector, which is 2, eigenvalue, times the second eigenvector, which is S times this vector. Again, S will go to C2, so this S will be in C2. So minus 2, 1, 4, plus C3 e to the third eigenvalue, 3t, times the third eigenvector. Again, we ignore this S and just write the vector, so this S will be in C3. So this is general solution of this homogeneous system. And now we have to find the constants using the initial value. So using x0 is minus 1, 0, 0, we can find C1, C2, and C3. So how we do this? We just substitute 0 instead of t, so all this e to the t will become just 1s. And x of 0 is given, minus 1, 0, 0, so we obtain minus 1. The first component will be the first component, minus 1, minus C1, minus 2C2, minus C3. The second component will be equal to the second component of this thing, so this is C1 plus C2 plus C3, and the same for the third component. This is 0, 2c1 plus 4c2 plus 4c3. So we have this system where c1, c2, and c3 are unknowns. So to solve this system, what can we do? We can, for example, add first and second equation to get c3 will be cancelled, c1 will be cancelled to get that minus 1 is minus c2. So we immediately get c2. Next, what can we do? For example, we can substitute c2, for example, in third and fourth equation. So we obtain the following system that c1 plus c3, c2 is 1, so we move it to the right, it's minus 1, and 2c1 plus 4c3 is minus 4. In fact, we can cancel the second one by 2, so we get c1 plus c3 is minus 1, and dividing by 2 we get c1 plus 2c3 is minus 2, and then we can say take minus of these two equations. So second minus first, we get immediately c3 minus 2 minus minus 1 is plus 1, so c3 is minus 1, and from any of this equation you can easily get that c1 is 0. So now we can write the solution of this. Just substituting c1 is 0, c2, so x of t now is c2 is 1, so e of 2t times this vector minus 2, 1, 4, and c3 is minus 1, so minus e to the, sorry, it's plus, e to the 3t times this vector here, minus 1, 1, 4. So this is solution of initial value problem. So solution of this thing, of initial value problem.